Okay, let's put it all together and look at these exit problems. Number one, the graph of the function f of x equals 9 minus x squared is given below. Which of the following definite integrals yields the area of the shaded region? So I've got a function, 9 minus x squared. It looks like I'm trying to capture the area bounded by it and the x-axis from -3 to 3. And so as I look down here, you could see that the only one that is doing so is choice A. So the definite integral of 9 minus x squared from -3 to 3 is exactly what we see in this picture. Okay, let's go on to number 2. In this one I said sketch the region whose area is given by the definite integral and then use a geometric formula to evaluate the integral. And the reality is right now this is all we can really rely on to evaluate these definite integrals. And like I mentioned in the previous video, that's going to change in the next section when we talk about the fundamental theorem of calculus. But right now, when we see this, we need to kind of say, okay, this is the equation of some geometric shape that we're familiar with. And at first, when you look at this, you might not realize that that is a geometric shape that you're familiar with. But I'm going to remind you here that this is what the setup for a semicircle would be. Remember, circles are always set up as like, x squared plus y squared is equal to some radius squared. So if you ever solved for y in a circle, you get y is equal to plus or minus the square root of your radius squared minus x squared. And so whenever you get an equation like we have here, which is essentially y is equal to positive the square root of 169 minus its z squared, but you can think of it as x squared. It really doesn't matter. This is a semicircle with a radius. It's the positive part of the circle, so it's the top part of the circle. So it's a semicircle, and it's got a radius of 13 because 13 squared is equal to 169. And so what's really tricky about this, though, is I'm not saying find the net area bounded by the entire semicircle in the x-axis. And so if my picture is something like this, where this is like -13 to 13 or something like that, I'm not going for that total area. I'm actually going for the net area bounded by that semicircle in the x-axis between 0 and 13. So I'm just going for this area right here, which makes this a trap kind of question. A lot of people would find the area of the semicircle and they would be wrong, because in actuality we're trying to find the area of a quarter circle here, because if you're going from 0 to 13, you can see that this is the quarter of an entire circle. So I would do pi r squared, but then let's divide that by 4 in the end, because a semicircle would be pi r squared divided by 2, but remember, we're taking half of that semicircle, so you'd end up with 169 pi divided by 4, which is choice D here. So look for these semicircles a lot right now in the homework. You'll see those. You'll see some other geometric formulas that you'll be able to apply, but this is definitely a common one. Okay, let's go to number 3. And this one says the graph consists of line segments as shown in the figure. Let's evaluate the definite integral from 0 to 11 using geometry again. So here we're going to be using triangles and rectangles and things like that. Now what's key here is we're trying to find the net area bounded by the function in the x-axis. Now I see students take this image and all the time sketch in the wrong areas. But I'm going to show you right now the areas that we're looking for. So if we start here, we're going from 0 to 11, by the way. So at the end of this, I could even draw that line down. But if I'm starting here, I'm not looking for an area in here. Sometimes students will be like, oh yeah, we're finding an area in here or something. No, it's between the function and the x-axis. And so isn't that this region in here? And then if I want the area between the function and the x-axis, isn't it all of this area in here? And the function and the x-axis, it's this area in here. And then again, this area right there. So make sure that you're always getting the right area. It's always the area bounded by the function and the x-axis. So that's what is going to set you up for success in this question. So this is a small triangle, so base times height is 1 times 1, but we're going to take half of base times height. So half of 1 times 1 is just going to lead us to 1/2. So that's that piece right there. Now for this, I might break this up. I mean, you've got a trapezoid. I guess we could work with that, but instead of working with that, I'm going to just break this up into this triangle, and then a rectangle, and then another triangle. And so you can see that this rectangle would have this triangle would have a base of 2 and a height of 2. So half of 2 times 2, if we do half of 2 times 2, that's going to give us another 2. And then this one right here, if I just take a look at this rectangle, base is 1, height is 2, so my rectangle in here, this rectangle in here ends up being just 1 times 2. So we have another 2. And then this triangle, again, that's 2 times 2. You can see we have a little bit of symmetry in a sense. And so 2 times 2 would be 4. We're taking half of 2 times 2 again for another 2. And so now everything that I've completely darkened in is what we've contributed to our total. So now we have this triangle right here. So that height is -2. And remember, any areas below the x-axis are going to be negative. And so I should probably flag, let me go back and flag that original 1/2, because that's going to be a negative when we do compute the definite integral in the end. But my base here is 4. My height is 2. So if I say 4 times 2, I get in 8. Oh, I'm doing half of 4 times 2. And half of 4 times 2 is going to just give me 4. But again, that's going to be negative, as is that very first triangle. So the first triangle and then this triangle are producing negative contributions to my definite integral. And then this 1 times 1, and we're doing half of 1 times 1 because it's a triangle. That's equal to another 1/2. So as I compute the total here, you could just add this up where you make this, in fact, a negative, and you make this one a negative. And so you can see that this negative 1/2 from the beginning is actually going to offset with a positive 1/2 at the end. This -4 right here is going to offset with 2 of these 2's. And so it looks like we just end up with a +2 in the end. And so let me just check my answer key. Yes, final answer ends up being just C, which is a +2. So draw the regions that you're finding the area of, or shade those in, or just indicate to yourself what those regions are so that you make sure that you're finding the correct areas. And then again, the key here is anything that is below that x-axis, bounded by the function in the x-axis, that's going to be a negative contribution to your definite integral. Okay, so I hope this helps tackle that 5.3 homework now. Good luck.